Jai Hind everyone. I'm Jyoti Sharma once again in front of you, giving some notes and some lectures regarding electrical machines, which is Unit 4 from the subject Basic Electrical Engineering, which is having a subject code of KEE 101 according to AKTU. In the previous lectures of mine, in 6 of the lectures what we have discussed about electrical machines, in that we have all discussed regarding the DC machines, DC generators, the motors, their working concepts, their classifications, their applications. Then we have gone for AC machines. Then in AC machines we have seen we can be having 3-phase AC machines, we can be having single-phase AC machines. In case of 3-phase AC machines, we have seen 3-phase induction motor, which is having a wide range of applications as far as the practical applications goes with, right? So we have seen in case of 3-phase induction motor, how the construction goes for stator, for rotor. It is a singly excited machine, right? It is a singly excited motor, because we used to give supply, a 3-phase AC supply only to the stator, right? But because of the rotating magnetic field which is being produced because of this 3-phase AC supply, there would be a relative motion between the rotor conductors and the rotating magnetic field, because of which we'll be having an induced EMF in the rotor conductors and thereby producing the torque, right? Now, once again, with the 3-phase induction motor carried on, we have seen single-phase induction motor. The difference between the two: in case of single-phase induction motor, we have seen it is not self-starting, for the very reason that in a single-phase induction motor, there is no production of rotating magnetic field by its own, right? So, it is not able to produce a unidirectional torque at the starting. So, at the very starting, the single-phase induction motor is not able to self-start, right? For that, for providing an initial torque, for providing a starting torque, we have gone with many ways of starting the single-phase induction motor. We have seen that in lecture 6 of mine. We have seen that it can be started with the help of resistance split phase. It can be started by using a capacitor in parallel to the main winding. A capacitor start, capacitor run permanently if the capacitor is being connected, and the final case is shaded pole. We have seen which motor is having its application as the most. Likewise, in case of capacitor start, capacitor run, it used to gives us a better power factor improvement. It also used to give us a nice starting torque, right, near about 300% to 400% of the torque, the operating torque, right. Now, coming to the another machine, which is also an AC machine, a 3-phase AC machine, that is synchronous machine. As the name is suggesting, it is synchronous machine. That means this is the machine which will always be running at a synchronous speed. We have seen what a synchronous speed is, right? It is having a definite relationship between the frequency and the speed, right? That's why it is being called as synchronous. It is in synchronism with the frequency. So, we'll be seeing what a synchronous machine is, right? We'll be seeing its construction, what will be the principle of operation and EMF equation for a synchronous generator, and then the synchronous motor. Okay, now coming to what a synchronous machine is. So, simplifying, if at all I say, a synchronous machine is an AC rotating machine whose speed under the steady state condition is proportional to the frequency of the currents in its armature. Let it be generator, let it be a motor. The magnetic field created by the stator currents rotates at the synchronous speed, and that created by the field current on the rotor, it also rotates at the synchronous speed, and a steady torque is resulted. So these machines are called synchronous machines because they operate at a constant speed and constant frequencies under steady state conditions, right? Now the synchronous machines are commonly used as generators, especially in the power systems such as turbine generators or hydroelectric generators, and also in providing the grid power supply. Because the rotor speed is equal to the synchronous speed, right? So, or the rotating magnetic field, then the synchronous motor, they can be used in the situations where a constant speed drive is required. Now, if at all I go with the construction, the construction for a three-phase synchronous machine is very much similar to that of a DC. It is also, we have studied a DC generator. A DC generator is very much similar with an AC generator. Only the thing is that in case of DC, we are having a mechanical rectifier which used to rectify the internally developed AC into DC. That is what we used to call it as commutator, right? That is not present in a three-phase generator. That too, this time it's three-phase, right? So the construction is in more or less same, but with a slight change. What is the change, if at all I just say? We have seen most of the rotating machines what we are having, it used to have its two most important part as stator, rotor. One is stator, another one rotor. Now, in case of a DC machine, we have seen what is being placed at stator, the field or the armature. The field used to be stationary and the armature used to be at the rotor side. It used to rotate. Let it be a generator or a motor, right? In case of a DC. But in case of a three-phase synchronous machine, this construction is a bit reversed, right? What is reversed? In this case, the field is being made as rotor and the armature is being made as stator, right? And why this is being done so? Why we want to have a stationary armature when it comes to a synchronous machine? Can't we have an AC being generated? If at all I am going with a generator, can't I have an AC being generated just simply by keeping the field as stator and armature as rotor? I can, right? But why there is a requirement of having a stationary armature or a rotating field, right? Instead of rotating armature. So there are certain advantages, when it is concerned with the synchronous machine. Why do we want to have a stationary armature? Now, what are those advantages? This kind of arrangement it gives. It is easier to insulate a stationary winding for higher voltages because they are not subjected to centrifugal forces, right? Because we want to have high voltages would be collected if it is working as a generator. We want to have higher voltages being generated, right? At the armature side, right? Now, for higher voltages, I need to give in more insulation. So that becomes easier if that body which is working on higher voltages, which needs to be insulated for the higher voltages, that is a stationary member because it has to, the centrifugal forces subjected to it would be comparatively lesser. Also, the stationary three-phase armature can be directly connected to the load without going through the large unreliable slip rings and brushes assembly. If at all, this three-phase armature, if that would have been a rotationary part or it is working as a rotor, in that case, we need to provide the 3 slip rings and brush assembly, right? Either to connect a load or to connect it to the external load circuit. So in that case, we want to have the slip rings and brush assembly. Now, we know that with the addition of slip rings and brush assembly, the maintenance becomes very much a big issue, right? Also, only 2 slip rings are required for DC supply to the field winding if it is working on a rotor, right? Since the exciting current is also small, we are giving just 220 volts to the DC supply, which is as a DC supply to the field winding to get them excited. So since the exciting current would comparatively be smaller, so the slip rings and the brushes, these will be of lighter in weight and will be having a lower inertia, right? Fourth point, due to the simple and robust construction of the rotor, the higher speeds of the rotor with this DC field is possible. This increases the output obtainable from this machine for a given dimensions. Also, I can say if the armature is made stationary, it can be provided larger space for accommodating more number of conductors, and I require more number of conductors because I need to provide higher voltages, right? The ventilation for a stationary member, that is comparatively very much easier. A stationary member, that is armature over here, because armature, it is working at very high voltages. So if it would have been rotating, the ventilation would have been a difficult task. So once I made it to be a stationary subject, in that case the ventilation, the air cooling by providing just simple ducts, it becomes much more feasible. The ventilation becomes much more easier. The collection of current is also very much easier when this heavy weight stationary armature is at stationary compared to if at all it would have been at rotationary part. So there are many advantages when it comes to a synchronous motor or a synchronous generator. We know that the three-phase synchronous generator, it is also being called as alternators. These are the machines which are responsible for the production of electrical energy in any country, right? So this has to be considered very strongly, that why we in this synchronous machines, we need to have a stationary armature compared to a rotationary armature. Okay, so we have seen the advantages of this kind of construction. But exactly which kind of construction does this three-phase induction or three-phase synchronous machine follows? Once again, we have discussed that it used to have two parts. One is stator, one is rotor. In the stator, we used to have the armature, and in the rotor, we used to have the field. Okay, but how does the construction is all about, So in case of stator, if at all I just say, it is the stationary part of the machine and is built up of sheet steel laminations having slots on its inner periphery, right? The three-phase windings which are being placed in these slots, the armature windings is always connected in star and the neutral is connected to the ground. So it is as simple as that, right? As we have studied in case of induction also, right? So it will be connected in a three-phase winding. We'll be having a stator. Now once again coming to the rotor, it is there is a change in it. Once again, the rotor that carries the field winding we have discussed. The rotor is consisting of field winding, which is supplied the DC current through the two slip rings by a separate DC source. But here the rotor that can be, constructed in two different types. One is the salient pole type and another one is the non-salient, or which is also being called as cylindrical pole type. Now what happens in a salient type? As the name is suggesting, salient or the projecting poles. Now in case of the salient pole type or the projected pole types, as it can be seen in the figure, the poles are projected outwards. Till now the construction what we have seen, there we used to draw the poles like this. First pole, second pole, third pole and fourth pole, right? Or the number of poles may increase or decrease. So basically these are tending inwards. But the salient poles are the ones where the poles are projected outward, right? These are mounted on a large circular steel frame which is fixed to the shaft as shown in the figure. The individual field pole windings are connected in series in such a way that when the field windings is energized by the DC exciter, the adjacent poles have the opposite polarity. Otherwise, there is of no use. One is north, one is south, one is north, one is south. Now, the low speed alternators or the low speed generators, which are working for the range of 120 to 400 RPM or 500 RPM, such as those driven by the turbines, have the salient pole types motor due to the following reasons, right? What are the reasons for that? The salient field poles would cause an excessive windage loss if driven at high speed and would tend to produce the noise. Another reason is the salient pole construction cannot be made strong enough to withstand the mechanical stresses to which they may be subjected at high speeds, right? So, these are being characterized, if at all you just see, these are being characterized by larger diameter and smaller axial length, right? Once again, since the frequency is of 50 Hz which is required, so we must use the large number of poles on the rotor of the slow speed alternators. We have seen that, let it be generator, the frequency of the supply, that is proportional to the speed, or the speed is proportional to the frequency, 120 F by P, or F is just proportional to Ns, right? So, in that case, for the frequency which is required, for that we require the larger number of poles, Pn by 120. Right? So, for that, for having the 50 Hz, we want to have, because the speed is less, right? These are slow speed alternators. These would be working for the speeds of 120 to 400 or 500 RPM. So, for that, if the speed is low, I have to increase the number of poles. If the number of poles have to be increased, then the diameter has to be a larger one to provide the necessary space for the poles. That is why I said that these are being characterized by, as these are low speed rotors, so they always possess a larger diameter to provide the necessary space for the poles, so that the larger number of poles can be accommodated to achieve this frequency of generation. Consequently, if the large diameter is there, it has to be maintained with a shorter axial length. So, these are being characterized by larger diameters and a short axial length. Also, if you just see, here, the flux distribution is also not uniform. I am having the polar region, the interpolar region. These are the interpolar region, right? So, the flux distribution will not be normal. Here, I am having the armature construction. Here, I am having the armature outer to this, where the slots are inward. I am having the various slots. In these slots, the three-phase armature winding is being wound, which is connected in star always, right? So, in this case, if you just see, the flux distribution is, the air gap is not uniform throughout. Here I am having a minimum air gap, and this side in the interpolar region, I am having larger air gap, right? So, the air gap is not uniform. These are the characteristics of the salient pole generators. Coming to the non-salient pole types or the cylindrical type. As the name is suggesting here, the poles are not facing outward, these are not projecting outwards, these are just simply cylindrical. So, in this case, the rotor is made of the smooth, solid forged steel radial cylinder having the number of slots along the outer periphery. It can be seen, I am having the various slots being made. The field windings are embedded in these slots and are connected in series to the slip rings through which they are energized by the DC exciter. Then where do we have the poles then if the complete is slotted? But the regions forming the poles are usually left unslotted, which can be seen over here. This is the unslotted portion. The unslotted portion. So, these unslotted portions of the complete cylinder, this would be giving us the poles of the motor, right? And they do not project out from the rotor surface. That's why they are also being called as non-salient pole types. If at all now characterized, these are high speed alternators. These would be working with the range of 1500 to 3000 RPM. In fact, this is no range. This is either 1500 RPM or 3000 RPM and are driven by steam turbines, right? In the earlier case where we want to have, in the case of salient pole types, these were low speed alternators. So there the turbines which can be used were water turbines, right? Which will be giving us fairly a lower speed up to 500 RPM, right? But here, as these wants to be rotated with a higher speed, the maximum speed which can be attained is 3000 RPM. For that, we require the steam turbines, right? Or electric drives, electric motors. And they use these non-salient type rotors for the following reasons. This type of construction has mechanical robustness and gives the Lewis operation at higher speeds, which is not feasible in case of salient pole. The flux distribution around the periphery is nearly a sine wave, hence a better EMF waveform is obtained, right, compared to a salient pole. We have discussed that in case of salient pole, a non-uniform air gap is there. So the flux distribution is also not uniform. But here, as it is a cylindrical portion, so the flux distribution is normal. And also the sine wave that is nearly the waveform which what we are getting, that is nearly a sine wave. Okay. Now, since the steam turbines, they runs at high speed and a frequency of 50 Hz is required. So we don't require now many number of poles, right? So the number of poles requirement over here is less, right? It is either 2 or maximum 4, right? So we need a small number of poles on the rotors to have high speed alternators. That's why these types of alternators are also being called as turbo alternators. These are also being called as turbo alternators, right? So we can use not less than 2 poles, and this fixes the highest attainable speed for a frequency of 50 Hz, obviously, and for 2 poles it is going to be 3000 RPM. The next level would be for 4 pole, if at all it is there. For 50 Hz, once again it is going to be 1500 RPM. Once again, this is being characterized because I don't require much number of poles, so that's why it is being characterized by smaller diameters, but a large axial lengths, right, and a uniform air gap. Now, coming to, we have discussed the kinds, the constructions. Now, coming to what is the principle of operation and what is its CMF equation. So, the principle of operation is very much simple. We have discussed it many of the times. We have discussed when we were discussing single phase AC, generation of single phase AC, when we have discussed generation of 3-phase AC, when we have discussed DC generator, there also we have gone with the same principle. The only thing which changes, which I have started with, is in case of DC, the internally developed AC is being converted with the help of a mechanical rectifier, what we call is as commutator, which is not present over here. So, an alternator or an AC generator, it is a device which converts the mechanical energy into electrical energy, right? So, when we supply the magnetizing current by the DC shunt generator through the 2 slip rings, because the field magnets are rotating, right? Now, keeping in mind that the alternators that use a rotating magnetic field with a stationary armature. Now, when the rotor rotates, the stator conductors, which are static in this case, because alternator, we are having a static armature or a stationary armature, and the rotor is rotating, right? So, that will be cut by the magnetic flux. So, they have an induced EMF produced according to the Faraday's law of electromagnetic induction. And if a coil or the coil conductor or coil links with any changing flux, then obviously there is going to be an induced EMF in it, right? So, the principle of working is very much same, that is the Faraday's law of electromagnetic induction. We need to have, for an induced EMF to be occurring in case of stationary armature, we need to have a rate of change of flux or the cutting of the magnetic flux, which is being created by the rotating field, right? Okay, now what will be the magnitude of this induced EMF, right? Now this induced EMF that can be found by the equation what will be deriving. Now if we just will be going with certain terms which we are already familiar with, say if P is the number of poles, we know that, Z is the total number of conductors or the coil sides in series or in phase, per phase. This is the coil sides in series per phase. And also we know that Z is equals to 2T, where T is the number of turns or coils or turns per phase, right? Now, F is the frequency of the induced EMF in Hertz. Flux is given by phi, this is flux per pole in Webers. Then the rotor speed, that is given by N. Kp, that is being called as pitch factor or coil span factor, it is also being given sometimes as Kc. Kd is the distribution factor. Kf, the form factor, which is given by 1.11 for a sinusoidal wave, which we are working upon. N is the speed of the motor in the RPM, revolutions per minute. In that case, obviously, the speed of the motor in revolutions per second would be N by 60. And the time taken by the rotor to complete one revolution, that will be given by 1 upon N upon 60 or 60 by N seconds, right? That means in one revolution of the rotor, the total flux cut by each conductor in the stator poles is given by, obviously, phi into P, flux per pole into P, the number of poles. Now, according to the Faraday's law of electromagnetic induction, the EMF induced is proportional to the rate of change of flux. So, the average EMF induced per conductor, that will be given by d phi by dt. How can I give? Once again, d phi we have just derived it as phi p, dt as 60 by n, so that becomes phi n p by 60. We also know that the frequency of the induced EMF, that is F is equals to Pn by 120, right? What is this relation? In fact, we'll be deriving that, but for now, frequency is given by Pn by 120. There's a fixed relationship between frequency and the speed, or speed is given by 120 F by P. Substituting the value of the speed in the induced EMF, right, we'll be getting the average EMF induced per conductor is given by phi P by 60 into 120 F by P, that becomes 2 F phi volts. If there are Z conductors in series per phase, right, so that will be average EMF induced per conductor now would be twice of 2 phi F Z. Z is the total number of conductors, and I also know that in terms of turns per phase, it becomes Z equals to 2T. So, I am just substituting Z as 2T. So, my equation will become 4 phi Ft. This is the average EMF induced per conductor, but remember, this is a synchronous generator. It is going to generate an AC which will be specified in terms of RMS value. So, the RMS value of the EMF per phase obviously is given by the relation form factor multiplied by the average value. So, the form factor is 1.11 multiplied by 4 F phi T. So, the RMS value of the EMF per phase is given by 4.44 phi Ft volts. The obtained above equation is the actual value of the induced EMF for full pitched coil or concentrated coil, because here we haven't considered Kp and Kd, the pitch factor and the distribution factor. That means the coil is full pitched and is also concentrated. It is not distributed. However, for the voltage, if at all I just say that it is being short pitched or over pitched and is also distributed, then the EMF equation it gets modified because of the winding factors, right? So, the actual induced EMF per phase equation will become 4.44 Kp Kd phi Ft volts, where Kp is the coil span factor or pitch factor, Kd is the distribution factor. Combiningly these two, it is being called as the winding factors. This distribution factor is actually defined as the ratio of the EMF induced in the distributed winding in a phase to the EMF induced in the conductor in the concentrated winding, right? Similarly, the pitch factor or the coil span factor is defined as the ratio of the EMF induced when the winding is short pitched to the induced EMF when it is being full pitched, right? So, these are the two factors. Now, what is the relationship between the speed and the frequency what we were discussing? As we just see, for a one complete revolution that will produce one complete positive and negative pulse each cycle when the number of poles is 2. We have seen that, right? If at all I am having a 2 number of poles, similarly over here, if at all the number of poles are 2 and I am making a single conductor to rotate in between the vicinity, right? It is going for a one complete mechanical revolution. Then for that one complete mechanical revolution of it, I'll be getting a single cycle of induced EMF, right? So, for 360 degree of mechanical revolution, I'll be getting a 360 degree of electrical revolution. So, the frequency in cycles per second will depend directly on the speed or the number of revolutions per second of the rotating field, right? So, if the AC synchronous generator has multiple poles, say 2, 4, 6 or 8 poles, right? Then for the speed of 1 revolutions per second, RPM by 60, the frequency per revolution would be 1, 2, 3 or 4 cycles per revolution. That means for 2, 4, 6, it will become 1, 2, 3. That means P by 2, right? According to pole pair. So, the frequency per revolution is therefore equal to the number of pairs of poles. Since the frequency depends directly on the speed and also on the number of poles, so we will be getting the relation which can be kept in a single equation, that frequency is given by Pn by 120. So, the EMF induced in an alternator would be having a frequency of Pn by 120, where P is the number of poles of the generator, N is the speed at which the rotor of the generator is being rotated, and 120 is a constant. Similarly, from the same very relation when it comes to motor, which we will be seeing in the very next lecture, from the very fair relation what we are having between the frequency and the speed, for this, if at all I just say, it's an alternator. To maintain this frequency, to maintain frequency as 50 Hertz, we need, because the poles are constant, these are not moving, right, once constructed. Then the speed has to be governed so that a continuous 50 Hertz supply is being obtained. Similarly, when it comes to motor, right, we need to have the speed would be obtained 120 F by P. So, there what we have to do to have this speed, a continuous frequency Hertz supply has to be maintained. Otherwise, the speed will not be obtained. So, we have seen the concept of the frequency and the speed. In the coming lectures, we are going to study synchronous motor, its applications, its classifications, whether it is self-starting or not. Thanks for today's lecture. Thank you all.